Hello everyone. So we are ready to move into your last unit, unit number 4, and this will be your section number 1. So under this section, we're going to talk about geometrical optics. That means basically lights. So as we know that lights is belong to electromagnetic spectrum that we can see it from our visible eyes, right? So we usually have the lights from red to almost the violet region that will be around 700 to 400 nanometer wavelength range. So now light is an electromagnetic wave. So now although we say in wave, so light has two type of properties. One is the particle nature of the light, and the other one is the wave nature of the light. So now particle nature is very easy to understand. If you send the light through very small hole, then light will pass through that hole, and then if you project into the screen, you're just going to see the light on the screen. That means it is basically moving as a particle. So we can understand that easily. But where is the wave property? So now if you send the light with a very small hole that we can call it as a grating or the slit, if you send this light through the very small slit, then if you project that into the screen on the dark room, you're going to see fringes. That means you're going to see kind of pattern of the lights on the screen that can be diffraction and interference of the lights. So now this is where that Newtonian mechanics break down that you are not able to explain on that scenario. Then you need to use the quantum mechanics that we start with the double slit experiment in the that feature that we can see as the fringes cannot explain by using Newtonian mechanics. So now in this section, as I told you, we're going to discuss about geometrical optics. That means we're going to show a light as a ray. That means you can just make a line with the arrow to represent the lights. Okay, so now as you know that this chapter in your textbook going to be chapter 25. Chapter 25. So in under that chapter, we're going to basically discuss about the reflection, refraction, polarization we already done, and total internal reflection, and also like spherical mirrors or plane mirrors and lenses, because every day in life we are using those things in our life, but how do you explain those things? What is the physics behind those, all the things that we are using will be discussed in this section. Okay, so now let's move into my slides. Okay, so let me see that why this is not showing me back and forth. Okay, so now as you know that we have primary colors. As you already know that white color is basically combination of this all the colors that we can see as sunlight in outside, that is white, because it is a combination of all the colors that we can see in visible spectrum, right? So now red, green, and blue are primary colors, and the combination of those colors will create a complementary colors, as you can see it in here. But whole combination we have in this region is white light, right? So now as a simple example, you can see the objects in two ways. One way is if you have light source inside your home, we'll say light bulb. So you will see the light bulb from your eyes directly, right? That is one way that you can see it. Other way you can see it, you have light bulb, you have some objects inside your room. We'll say it is a dark room, you have only a light bulb, then you're going to see your book inside the room. So that case, what is happening is that light produced by the light bulb will hit the book, and then that will reflect back into your eye. Then you're going to see the things. That is the second method, the way that you can see the things. right? So now, geometrical optics will be just showing you the light as a ray, basically, right? So light we're going to represent by using the rays that basically describe the direction of the wave propagation. And also there is another thing that we call it as wave fronts. Wave fronts will be the surface passing through the point of wave that have the same phase and the amplitude. That means those are, we call it as wave fronts, right? So now this is the rays, right? Say ray is always perpendicular to these wave fronts. So these are coming from hygiene principles and those things that we are not going to discuss, but that's how usually rays we're going to define it as the light or geometrical optics. So now optical illusions, you guys have seen this many times. As a simple example, when you travel on hot day, you're going to see a pool mirage, right? That means you're going to see as a pool in the middle of the road. So these things happening because of refraction that we're going to discuss. Simple example is usually the when you have warmer air, your refractive index that we're going to discuss in a minute will be smaller. Because of that, you see that your bending of light will be different from when the road getting hot, then your refractive index getting lower, then you're going to see the refraction in your side. That's the basically pool mirage that you're going to see. And also another thing is that if somebody is inside the water, you're going to see basically, although she's sitting on the ground, you're going to see the foot in somewhere here, right? That is also an illusion that we can see, but really she's on the ground, right? And in addition to that, you guys know the rainbow. Rainbow has the colors, and there are primary rainbows, secondary rainbows. Why these things are happening? So especially in the concept of refraction that we're going to discuss. So now light can reflect and refract. Reflect means light is going backward. So to the same media, it will go back into the same media. We call it as the reflection. So if light go into the media, that means transmit to the next media, that is, we call it as the refraction. So now this is the experimental setup that we have. This is the light you're going to send. You see that this light going inside. This is, we call it as refraction. So light going backward into same media, we call it as the reflection. So that is very simple thing that you guys learn in your elementary school, right? But there are a couple of things you need to understand to analyze those kind of problems. One thing you need to realize is, how do you measure those angles? What is the procedure that we need to measure those angles? Procedure that you need to follow. So if I have a light hit on this media, you're going to make a normal line first. That is the 90 degrees line that I have labeled it as normal line. And then you're going to send the light. That light will hit the media with the angle that I have θ1. That is, we call it as incident angle. Important thing is you measured that angle with respect to the normal line. So that is the incident angle is. And then this light will reflect to the same media. Then that angle again with respect to the normal line you drawn will be your reflection angle. I don't have it in here. This is reflection angle, right? So now the light go through the media will make angle with respect to the normal again. That is, we call it as refraction angle. So now I have incident, reflection, refraction. These all three angles you need to measure with respect to your normal line that you have drawn. Okay. Okay, so that is one thing. And in addition to that, when light go through the media, there is very specific thing that's happening. That light bending behavior, you see that sometimes light will bend differently. So simple example, if I have air water media, then your direct light is going to bend towards the normal. Your direct light is where direct light will be basically this line. So it's not going on that line, it's going to bend towards the normal, bend towards the normal. So that will happen when there is a water media has the larger refractive index. So refractive index is, we use the letter N. Refractive index is an index, there is no units, but definition of refractive index is basically ratio of speed of light in the vacuum, that is the speed that we talked last time, 3 times 10 to the power 8, to the ratio of speed of light inside that media. So that is what the N means. N means speed of light on the vacuum divided by speed of the light on the media. So that is the N definition, refractive index definition. So now this bending behavior is depend on what is your refractive index of the media that you're going to hit, right? So now this is the case that if N2 is greater than N1, right? But if you have the source on the water and then it will hit in here, then you will see your light is bending outward from the normal, not direct light, bending outward from the normal line. Then that will be basically because your air refractive index is lower than the your starting media. Because of that, you're going to bend outward from the normal. Okay, so you need to understand that very clearly. It depends on the speed of the light go through that media. Okay, okay, so more information about refraction. So index of refraction we define as we did it in earlier. It's obvious, right? And then when your light go through the media, so your velocity and the wavelength going to change, but your frequency is going to remain constant. You remember that velocity equal frequency times wavelength. So two parameters should be changed. That will be the velocity and the wavelength. But frequency going to keep constant when it go through the medias. Okay. So within that knowledge, let's talk about the two laws that is related to reflection and refraction. So now law of reflection is the first thing you're going to discuss. Law of reflection is saying that incident angle will be equal to reflection angle. Remember in the diagram, incident angle, this angle is equal to reflection angle. That is called it as the law of reflection. And it's very simple thing. That means if you see any reflection of the light, you know that the normal angle, the angle that create in between incident and the normal line will be equal to the reflection times the normal lines. So that's called it as the law of reflection. So now law of refraction. So law of refraction is explaining the refraction information. That means if you have a media that has the index N2, and if you go to second media, you will be able to write by using this connection of refractive index and sine of theta values. What that means. As a simple example, in this case, you will be able to write, you start with the N1 media, it's the top media, right? You start with N1 and then take the sine of incident angle, that is theta 1 in here. This is your incident angle, should be equal to second media times sine of your refraction angle theta 2. So that is, we call it as the law of refraction, because it is depend on the refraction index, and theta angle also depend on those properties of the material. So now sometime we call it as the Snell's law, the refraction law. right? These are the two laws. In addition to that, there is actually first law that I did not include in here, that saying that all the drawing that you are doing will happen in the single plane. That means if I have a light coming in here, that light should go in there. That means I will be able to draw it on the single plane on the refraction and reflection. It's not bending to the different plane. Okay, so everything is on the single plane. That is first law, and second one is the law of reflection, and third one is the law of refraction. So now a little more about this refractive index and the wave traveling into second media. So when I have a wavelength, we know what is the wavelength is in your physics 1 class, we discuss it. Crest to crest distance of the wave, we call it as the wavelength. Right, so now when wave travel in first media to second media, this is media number 1, this is media number 2, you will see that your frequency will keep constant. Frequency measured in basically your time axis of the wave, right? Period of the wave, 1 over period, we call it as frequency. So that will keep constant, but your wavelength is decreased when you go to the second media if second media has greater refractive index. I'm talking if N2 is greater than N1 case, right? Otherwise, it will be opposite. So now, since we know that the N2 is greater, then we know that the V2 should be smaller, because definition of N is C divided by V. Because of when N is greater, my V2 should be lower. So now velocity in this media is less than the velocity of this media to make it everything make sense. Okay, so keep frequency constant, but velocity decrease and wavelength decrease to make your velocity equal frequency times wavelength equation. Okay, so now as we know, refractive index will be different for different medias. For the vacuum, we will be exactly C, because C is the speed of the light on the vacuum. Then C cancel out, your answer will be 1. That's why we have vacuum 1. Right, so air is little greater than 1, other all are different, and also since V is always less than the speed of light, N will be always less than, always greater than 1. N is always greater than 1 because your numerator is always greater than denominator. Okay, all the numbers you can see it in here. Okay, so now again, I'm going to move into the refraction. So reflection, there is nothing we need to talk because its angles are same. We're going to discuss that when we come to the mirrors. But here is the reflection. So now, as I mentioned, if your both media are the same, then light will be a direct light, no bending at all. So this is going through exactly same way as it come to the media. So, but if your N2 is greater, then your light is bending towards the normal. That's why light bending this way, right? When N2 is smaller, your light is bending outward from the normal. Okay, so I think everybody understand these features of the refractive index. And so now we're going to move into chromatic dispersion. So chromatic dispersion means basically different colors light going to bend different ways. So that is, we call it as because of they have different wavelength. So that is called it as a dispersion. In addition to that, you definitely need to understand monochromatic light. Monochromatic light means single color light. If you go to the experiment in the laboratory, you're going to use monochromatic light. That is a laser beam that has single color, right? So now, when you have the white light, we know it is combination of the colors. So now what happen is, if you project that into a glass media, you have seen this color spectrum through the rainbow, and probably through the automobile glasses, that when you drive, you will see the colors project into your clothes with these red to violet colors. different colors. Why this is happening? Because of they have different wavelength and they are traveling in different velocities. Then you're going to see the bending behavior of those colors, separate colors, right? So now it is very important that your red light from your spectrum, red is the fastest light. Red is moving faster than the other lights. The violet or the last color will be the slowest color, right? So I have the red and green, red and blue, blue as the lowest and red as the highest speed. So because of that reason, you see that red is bending less and red is always very close to the direct light, very close to the direct light always. So now this is for N2 is greater than N1, this diagram, N2 is greater than N1. And my next diagram is N2 is less than N1. Is still, although it is bending outward, your red is keeping close to the direct light because of the speed of the red is greater. Okay. So now rainbow spectrum that you are seeing also happen in the same features, because when the raindrops are falling down, your light going to be refract, and your first drop that you are getting in here will have a red and the green, red and the blue. Your spectrum will be in between, and then the top dot may have a red and blue again, but the where that you are watching in your angle, you're going to see the color of a spectrum with the red on the top and blue in the bottom, right? So that usually happen around 42 degrees. But do you ever see the secondary rainbow? So you definitely will see lower intensity because first one is more intense than the second one, but still it is possible. So now around 52 degrees, you're going to see a secondary spectrum, but it is very important that in secondary spectrum, you're going to see the opposite colors. So next time watch when you see the secondary spectrum. So what is happening is actually your raindrop, the sunlight happening in the bottom of the one will be doing the reflection on here. You see refraction in here. You have the blue and the red, and then you have red and blue. Then you have the blue on the top and red in the bottom. So that's the reason that you will see your secondary spectrum red to blue and primary one blue to red. Yeah, we'll show the opposite colors. Okay, so now we have some idea about reflection and refraction. This is just for you to understand that we are talking about actually specular reflection. That means you have a smooth surface. And this is the one that we're going to focus on. But your reflection can be happen in diffuse reflection when your flow is not smooth. Okay. So now total internal reflection. It is another important concept by wordings. It says basically total internal reflection means no refraction. No refraction. That's what the total internal reflection means. Okay. But what is actually happening in here? So simple example, this is a real experiment that we can see it, but this is the cartoon of that. If you have a light source in here, to happen the total internal reflection, your source should be greater refractive index than the other media. So you're going to start in here, you have glass and air. You're going to start your object or your source inside the glass because glass has greater refractive index. This is happening only in that case. Okay. So now if I have the source in here, when I keep it on the 90 degrees on this plane, then that light will be just going 90 degrees to that. It is exactly my normal, right? But if I tilted it a little bit, then you're going to see, if I tilted it a little bit, then you're going to see this is my refraction. So refraction, and this is my refraction, the reflection and refraction, right? So now when you angle make a little larger, then again I have reflection and refraction. and again reflection and refraction. Now I keep tilting my source to make different angles. When I do that, there is very specific case in happening in this case. That will be somewhere here. What is happening in here is, basically you will see that you increase the angle, but at this particular angle, you're going to see your refraction exactly going on top of the media. So that means no refraction. So that is, we call it as total internal reflection. At that time, your incident angle, we call it as sorry that this will keep doing that. So incident angle, we call it as critical angle. So now if you go and write Snell's law at this point, E point, right? If I write it at E point, so that will be, you're going to start with N2, I would say glass in here, N2 sine of theta critical should be equal to N1, that is my pulse media, times sine of 90 degrees, because my angle in here is 90. This angle is 90 degrees, right? So now sine 90, as we all know, it is just 1. Then you can calculate the critical angle by using sine inverse, and you're going to do divide by N2 first, and then you take the sine inverse of that N1 over N2. If I take my media in here as N2 and okay. So now that is called it as a critical angle. Now somebody, when you read it, you will see this different, because in this derivation, N1 is taken as your glass and N2 is taken as air. It doesn't matter, whichever you have, you write your Snell's law correctly, then you can get the correct answer. Okay, so in this scenario, your N2 should be the second media, although I take the N2 as my first media. That's why it is opposite in here. Okay, anyway, so now that will be your that will be total internal reflection. Now, a total internal reflection have many application. In your childhood, you have used the binoculars, so that is the total internal reflection behaviors. And in addition to that, fiber optics and some microscopes, we have those, because as example, if you need to watch your cells inside the body, that microscope that we're going to send should be able to see whole thing as a without refraction. So in that case, we use it as the total internal reflection information. And polarization we discussed earlier too, polarization by reflection in here. In this case, actually, when you have unpolarized light, if you send that light to the media, so then your reflected light going to be totally polarized at some specific angle. This one going to be totally polarized, but the other one going to be partially polarized. So polarized or partially polarized, it doesn't matter. But important thing is reflected ray going to be fully polarized. At that time, we call it as the angle that I have it in here. We call it as theta B. That is call it as Brewster angle. Okay. So now you can use the again your refraction law or the Snell law in here, and then you will be able to write it by using your theta B angle. Then you will be able to derive this equation. We call it as the Brewster angle. When the Brewster angle happens, when your reflected light is fully polarized. Okay. Okay, so now we're going to move into the images. So you will see the image usually from the mirror, from the lenses, but there are basically two types of the images that we can see. One we call it as the real image, other one we call it as the virtual image. So now it is very important that you understand the difference between these two, right? So real image means by hitting the light, right? As a simple example, if I have an object in front of me, I am going to see the object by reflection of the light, because there is real light. That is, we call it as the real image. It is a intersection of real light will be real image. Okay, and next one is the virtual image. Virtual image will be the image. Simple example, in the mirror. When you sit in front of the mirror, you're going to see inside the mirror your image. That is virtual. There is no light going inside the mirrors. So that means you basically going to extend the light, and extended light going to intersect. That we call it as the virtual image. So now example here. This is the virtual image. So we're going to use extended light by dotted line, and real light, we're going to use it as a straight light. Okay, real. Okay, this is how we're going to represent virtual and real in your drawing. So now, first one is the plane mirror that we're going to discuss. So plane mirror is simply a flat mirror that you will see it in your bathrooms, right? So in the plane mirror, what you basically observe when you sit in front of the mirror, you're going to see you inside the mirror almost same size and same distance, right? You're going to see exactly same size, same distance, this number and this number. I'm going to write not the P, I'm going to write DI and sorry, D naught and DI. So DI and D naught are the symbols that we're going to use to represent object distance is D naught, and DI is the image distance. Over the time in optics, the measurements that we are taking, there is no vectors, but important thing is you measured always with the to the lens, to the mirror, to the spherical mirror. That distance is measured to the device that we're going to use. Okay, so now if I have object in here, this is how the light will travel. It will go to the mirror, and then you're going to see that light in your eyes. Then you're going to extend those light. That will be your image. Now you will see virtual image in this case. Okay, so that is, we call it as the plane mirror. So now three properties that we discuss in plane mirror. Yeah, before that, let's move into this one, and then we can come back to that. So now the things that I am talking in here is go not only to the plane mirror, it will go into the other mirrors and also lenses that we're going to talk throughout this section. So magnification, what is the magnification means? Magnification means basically if you measure the height of the object and if you measure the height of the image, if you take the ratio to height of the image to object, we call it as magnification, HI over H naught. HI is the image of the height, H naught is the image of the object. So now that will be exactly equal to the image distance divided by object distance with the negative sign. Okay, so this is, we call it as the magnification. So this negative sign will give you the information at the end. After all the calculation, if you get M is negative, we call it as inverted image. Inverted image means if you orientation is this, but you're going to see this orientation, then this called as inverted image if your magnification is negative. Okay, now let's summarize the plane mirror. So now plane mirror has some properties, right? Image distance equal to the object distance. That means your D naught equal DI. Okay, and image is unmagnified. Unmagnified means your M, if you calculate, since DI and D naught are equal to each other, that will be a -1. You remember that negative in front of that. This -1, no, this is +1 because your DI is negative. Then you're going to get the upright image. Okay, and your image is virtual. Why it is virtual? Because your DI going to be a negative value in this calculation. After you calculate, this will be a negative. Then it will be virtual. The image is not inverted. Left and right will be reversed in the plane mirror. You can go and lift your right, as you can see it in your screen here. This is my right, but you see it as left. Okay, that will be plane mirror. Okay, so now we're going to move into the spherical mirror. For this, see this section, you can take the break in your side and come back and watch it, right? I'm going to continue because this will be a little longer session. And spherical mirrors. So mirrors can have concave and convex mirrors. What that means is your curve in features that you will see if you have the mirror like this, that you're going to make a circle, something like this, then if your object is in this side to that mirror, we call it as caved mirror because it is caved towards your side. This is the caved mirror. So we usually use the mirrors in this symbol. What that means is on other side of the mirror is plate that you cannot bring the light to that side by using mercury or some materials that can reflect the lights, right? So now concave mirror is caved towards the object. Now when you see the when you draw the mirrors, it's mirrors or lenses is very important. So this is, we call it as principal axis. Principal axis is basically perpendicular axis that you draw to the your device, and then center of the your mirror, because if this is basically arc of the whole circle, right? But what is the whole circle center will be staying on your this side, that is we call it as center, right? So then other one is the convex mirror. Convex mirror means usually you have the features like you have like bending the plex out from the object, right? You're going to have a mirror like this, but your object going to sit somewhere here. So now to the object, it is plex out. So that is, we call it as convex mirrors. That means your object will going to stay somewhere here, right? But in this this mirror, your center will be sitting on this side, right? That's why your center is here. Okay, so now spherical mirrors divide into these two parts, concave and convex. We're going to analyze more about that. But before moving into that, there is a point, we call it as focal point. Focal point is basically when you send the parallel light to the mirror, all the light will be focused into one point. That is, we call it as the focal point. But by experimentally, we can find it out that this focal point is exactly half of the radius. Radius is basically distance from lens to mirror to your center, right? If you take the half of that, that will be the focal point. So now focal point for the concave mirror is the positive, but focal point for the convex mirror is negative. Okay, so keep those in mind. Okay, so now spherical mirrors, we discussed about three things. One is the object distance, image distance, and focal distance, and also radius, right? So in addition to that, we discussed about height of the object and height of the image. Those things are important notation that we're going to use those notation throughout your rest of your semester, basically, right? So now we discuss about two mirrors, concave and convex mirrors. So now for the concave, convex mirrors, let's skip this slide, come back to that later. So now let's focus into focal point first, right? So now I mentioned that focal point is half of the radius earlier, but how to find it? When you go to the experiment, you're going to find the focal point of concave mirror, convex mirror, convergent lens, and divergent lens, right? So now this is for your concave mirror. If you send the parallel light to this mirror, you're going to send the parallel light to the mirror. When you send many rays parallel to the mirror, what happens is all the rays will going to reflect. You remember that the reflection law that we discussed in, that means normal for your spherical mirror will be this. Normal will be basically radius. right? Not like in the plane that we have a normal 90 degrees. Here 90 degrees will be made with the tangent to the radius, right? So now your angle that will incident will be this one, reflection will be this one, then according to the rule that should go through the focal point. So that happened to all the rays. That point is, we call it as the focal point, that you can experimentally find it out for your lens, your mirror, right? And then convex mirror will behave little different. The reason is, when you send the parallel light, your center is in other side. Now, if you draw your 90 action will be the same. In that case, actually your rays that reflect back will not intersect on the left side on this mirror. What happens is, you need to draw the extended light. That is what the focal point is. That's why the focal point for the convex mirror is a negative value. Okay. Okay, so now let's move into the next one. So now ray tracing. So how are you going to draw the things? It's very important that you practice it yourself to understand how to use the rays to locate the image. So now we're going to do it for the convex mirrors and concave mirrors. But before moving into that, I will show you how to do that. But before moving into that, I need to mention about this equation. This equation, we call it as the mirror and lens equation. That is useful for mirrors and lenses also. Exactly same equation. This is magnification equation that we discussed, will work for mirrors and lenses. So now it's very simple. You know all the notation in here. So keep those notation on your head always. Okay. So now I'm going to skip this also. Now let's move into a little bit about this equation. So now this equation has some informations, right? So now if you do it for this sign convention of those will be very useful. One thing you need to remember is your F is a negative value for the convex mirror, right? So that is very important. Other than that, F is positive. So now, according to your calculation, by using M, you can decide that if M is positive, that will be upright image. That means same orientation. M is negative, that will give you the inverted image at the end, right? So in addition to that, after you plug the numbers into there, if you need to calculate the image position, if that image position is positive, that means your image is real. Okay. If image DI is negative, that means it is virtual image. So those all are theoretical calculation. By using this analytical method, this is, we call it as analytical method, you will be able to understand what kind of image you're going to see from that device, right? Those are the things that I explain in here. You need to keep those in mind and make sure that you basically follow those informations throughout the course. So now concave mirror is the first one that I'm going to study. So now drawing ray diagram, as you can see earlier, there are many diagrams that I have it in the slide, but I'm going to draw it in my hand, and bear with me because it is a little hard to draw in the screen. Okay. So now concave mirror, as we know, it is looks like this, right? So first thing is, you need to draw your principal axis or optical axis. Next thing is, you need to take the focal point and double of that, we call it as the center, right? So now you can have the image in front of the mirror. We are not going to keep the object in the back side of the mirror. You are not going to see anything. So you always keep the object in front of the mirror. So you're going to keep the object in front of the mirror. Everywhere you can keep it. You can keep it outside C. You can keep in between C and F. You can keep in between mirror and the F. These diagrams will be different in different locations that you need to practice, right? So I'm going to keep the, on my example, I'm going to keep my object somewhere here. Object. Okay. So now there are 4 rays defined to locate the image. To locate the image, there are 4 rays defined that you can use any of 2, you know, that we just need to get the intersection of 2 rays. So we need only 2, but there are 4 rays defined. Those are the 4 that I'm going to draw it in here. Okay. So now first ray will be, you're going to draw parallel light to the mirror. So this light, as you guys remember, should go through the focal point. That's where that we define the focal point. Then this light will be going through the focal point. That is my number 1 ray. So that is easier ray that everybody can draw it, right? Now second ray will be exactly opposite of this. What that means, you're going to send the light through the focal point to the mirror. That will be reflect back with the parallel to the axis. So now you're going to send the light through the focal. It should be a straight line. It is not easy for me to draw it in here. Okay, so then this light will go parallel to the axis. That is the second one. Okay, because of drawing bad, you will get the different places. But if you do the ruler and the protector to do that, it will give you the exact theoretical answer. Okay, that is my second one, right? So now third one is saying that if this is the actually without protector, that I cannot do it, but I'm going to try to do it. Third one will be if you send the light to the center or the vertex point of this mirror, that light will be exactly go with the same angle in the place. So that means it will be going through this. So that is the third one, right? So should be all of them should be intersect on this place, although my one is little away that I cannot easily draw that. I'm going to probably take this off and redraw again to make it little good. Okay, that is the third one. Okay, so now fourth one will be drawing through your center, because the center, you know, that if I send to the normal line, that should be definitely go on top of that. That is the third one. I need to extend this mirror. So you can always extend the mirror as you want to draw your diagram. So now next one, you send through the center. I know that it is not easy to do it in my case. I will not do that in here because it will not go through the point that I need. Okay, because of that, I will leave that as it is. So there is fourth ray. Fourth ray will be go through the focal, go through the center, will be reflect back on top of that. Okay, so that means don't take this as a best example because my drawing is out of place. Okay, but what I mean is if I send the if I send the through the point to the mirror, so this should go back on that. That means actually this point should be moving to the left little bit to make it to correct place, right? If I do by using protectors and the rulers, I'm going to get into the exact same intersect point. That is where your image is located. So this is where your image going to be located. Okay, those are the 4 rays that we can draw for concave mirror and also convex mirror. I'm going to come back to the convex mirror in a minute, but let's move into some drawings. So now here I have the object somewhere further away from the your radius point or C. So somebody can say C or R, doesn't matter, twice of F, right? Radius point. Now in this case, take a look. I'm going to draw 2 rays. First one, parallel to the axis, go through the focal point, and second one, go through the focal point, will be parallel to the axis. Now where is the intersection? It is in here. Your eye is here, right? Then you're going to say that you start tip point. This is where the tip ending. So that means your image will be somewhere here. Okay, farther away from the radius. Now in second diagram, I have the object exactly at center. This is at exactly center. Now let's see the ray diagram. First ray and second one. And you will see exactly same point, but inverted image. Same size, inverted image on exactly the same place when you keep the object at radius position, right? So now I have the object in between C and F. This is what I tried to draw earlier by hand, right? Because of my drawing is not easy to do in the screen, we did not get the exact position. So now in this case, take a look, parallel ray, go through the F, and next one, go through the your F and parallel to the axis. Then you see the image location somewhere here. So now again inverted, but larger in size. Okay, and now you have the object at the focal point. This is very important situation, and you will see first ray, and this is my second ray. So this is where you're going to observe. You know that these two rays will never meet because of that no image on that one. There is no image. This is very special situation that we do not see the image. Okay. And then next situation is inside the focal point, in between mirror and the focal point. This is also a very specific case that we can see magnification. So magnifying mirrors. First ray and extend the first ray because I know that I need it. This is second ray, and this is where you're going to see it. They will never meet on the left side, but they're going to meet on the right side. If I extend the light, those will be creating the magnifying image larger in size and also upright. It's a very specific case that we can use as a magnifying mirror. Okay, so final conclusion, by using concave mirrors, you're going to see this different pattern. If you sit on the your classroom, if your instructor going to bring the big concave mirror towards you, you're going to see yourself in different orientation, larger in size, smaller in size, moving back and forth. Sometimes you don't even see the image. That is the behavior of concave mirrors. Okay. Okay, so now convex mirrors. Right, we're going to do exactly same thing, 4 rays for the convex mirror. So now convex mirror, we have this shape, flex out from the object, and again your optical axis and your focal point and the center, right? So we're going to keep the object always in front of the mirror. So now first ray, as we discussed, you're going to send the light to the mirror. That light should not go to the other side because mirror is not prohibited for you to go to the other side of the mirror lens, the rays, right? Because of that, according to the rule, this should be reflect back, like go through the focal point, but going to reflect back. That is the ray number 1, right? So now ray number 2 will be exactly opposite, but since I don't have the focal point on the left side, that means I need to send this light to the focal point, like sending towards the focal point, but light will not go in that side. Light will going to reflect to the parallel to the axis. The bad drawing too. Right, then this is your extended light. That means the image that you're going to create for this will be somewhere here. It is virtual because it's an extended light. Okay. So now other 2 rays also you can draw. Sorry, so go back. And other 2 rays also you will be able to draw. The third one is you send to the center, right? That means you're going to send to the center. So that should reflect back this way. That is the third one. And fourth one, you're going to send to the center. So this is always hard to draw in the drawing. So you're going to send it to the center, right? So that means this is where the center is. But if you send the light exactly to the center, it will hit and reflect back. This everything will be your tip point of your image. This is where the image located. Again, you need only two of them to represent the location of the image. Okay, so now let's go to next slide. I have some drawing. First one and second one, I extend the light, and second one, and that will be extended light, and it will create the image somewhere there, similar to my diagram that I have drawn. And then you're going to keep the object in different places. So you draw it yourself, and you're going to see they will not change. They will exactly keep the same kind of diagram. Only thing is happening is just going back and forth your image. Other than that, you are observing exactly same image, virtual, smaller in size, upright, right? Nothing changed. Only thing is change is just going back and forth little bit. You see, so here, 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 and here. It is always virtual, smaller in size, upright, always creating between vertex point and the focal point. So that means convex mirrors is only have the same properties. It will not change by changing the position of the object. Okay. So now let's summarize convex and concave mirrors. So one important thing is you need to identify is these features. Convex mirror has negative focal point. Concave mirror, you have positive focal point. And convex mirror always create virtual any object and reduce in size, smaller in size. And di is always negative because it is virtual. And concave mirror, any of these possibilities can happen according to the place of the object. So this also can be greater in size, smaller in size, depending on the location of the object. So that is for the concave mirrors. Okay, so now before moving into lenses, we discussed about the plane mirror, concave mirror, and convex mirrors, right? This all we can use the same equation, same magnifying formula for calculation, analytical calculation. Drawing will be exactly same, but you need to keep track on that 4 rays, how to draw them, right? In addition to that, there are many applications. So plane mirror, you already know your bathroom, we're going to use it, plane mirrors always. And concave and convex mirrors, concave mirror we use for the magnifying mirrors, like you see 3x, 5x, 8x mirrors, those are concave mirrors, right? So and in addition to that, you can see those mirrors probably in your headlight of the cars, you will see the mirror. And also satellite dishes that you will see the mirrors, those are concave mirrors. So convex mirrors are rear view mirrors that you have it in automobiles will be convex mirrors, because we want to see real object. We don't care about the size. We don't care about the orientation. We care about the orientation, and because we just need to see what kind of vehicle coming on the my right side or left side by watching the rear view mirrors. That purpose can do by using convex. If you use concave mirror for that purpose, you're going to see vehicles coming out from upright inverted images, larger in size, smaller in size. Sometimes you don't see it. That is not what we are expecting in rear view mirrors. Because of that, we use convex mirrors for those. Okay, and now let's move into lenses. Okay, so lenses is a kind of glass piece that you can have in very small thickness. We call it as thin lenses. Okay, so that can have this shape, that can have this shape. So first shape we call it as converging lens, and second one we call it as diverging lens. And the equation you will see here, because you know that there are two surfaces, right? Curved inward, curved outward. These two surfaces can have two different radius. So they can made from different materials. If it is a glass, it will be glass. If it is a different media, then you need to take it in as a the different media. So now this n need to be replaced according to whatever you are using, right? So now since I have n in here, that will be for the material n divided by the AR, that I'm thinking that I'm going to keep it inside the AR. That means I have basically n over AR refractive index, right? If it is the different media, then definitely you need to use n over n media for n. That you need to replace this n with this. Okay. So this is called it as lens maker rule, that we are not going to actually use it. It is the lens maker rule when they develop the lenses. Okay. So now this equation we already know and we discussed. That will be exactly same for the lenses too. So we're going to work with thin lenses, as I mentioned. That means very small thickness lenses. So we're going to focus into converging and diverging. Some people call it as double convex for the converging. Some people call it as biconcave for the diverging. I'm going to use converging and diverging. Converging for this one, diverging for this one. Okay. So we are not going to talk about these parts in your class. Okay, so now again, ray tracing is important concept. So now for lenses, since light can go to the other side of the lens, then I should have a focal point that side and focal point this side. Center on this side and center on this side. Because of that, you have two centers and two focal points because you have two surfaces basically, right? So now it is very important to understand light can go to the other side. Because of that, if I send the light to the converging lens, this light will be focused into the focal point on the other side. That is, we call it as important focal point for the drawing. If you keep the object on the left side, your important focal point will be on the right side. But if it is the diverging lens, if you send the light, the important focal point will be on the left side. And also it is the light, extended light, going to merge into that place. Because of that, this focal point is negative. F is negative in this case. Okay, in this case, F is positive. Similar to your concave mirror, right? So now that will be your important focal point, but other side also there is a focal point. Okay, and in addition to that, you can calculate the power of the lens by using just reciprocal of the focal point. So now it's very important in lenses to see that how refraction work inside. So I'm going to focus this light in here to zoom in picture in here. What is actually happening? Converging means light going to converge, right? That is why it is happening in here. You have air and you have glass. Now you have normal in this dotted line. Light is bending towards the normal. So now I have glass and air. Now light should be bending away from the normal. Because of that, this light going to converge. That is how the inside of these lenses will work. Although we are not going to draw that in real life, that is how it will work. Okay, and diverging lens, if I zoom in this picture, what happens is you have again air, glass, and air. So air to glass bending towards the normal, and then glass to air bending outward from the normal. That's why it diverge. Diverge means it's going outward from the axis, right? So now that will be enlarged picture of the diverging lens. But in our life, we are not going to draw these inside things because it is very hard to draw inside that way. What we're going to do is we just going to make this line, and then we just going to draw this light and this light only, ignoring the what is happening in the middle. After you know the conceptually what is happening, you can just draw incoming wave and outgoing wave. So that should be good enough for drawing. Okay. So now again, there are three rays that we can use to draw the ray diagram. So or understand the location of the image. I'm going to show that in next slide. can skip this one. So now this equation is the same for the lenses also, right? It is very important again, this F will be negative for the diverging and positive for the converging, and M have the same definition as mirrors. If it is negative, inverted image. If it is positive, it is upright image. And DI also have the same information as the mirror. Okay, so those information we're going to keep track on. If DI is negative, that's a virtual image. If DI is positive, that will be real image. Okay, so magnification rule, as we discussed, it is exactly the same for the lenses too. Okay, so now drawing. Okay, so now lenses, we have only 3 defined rays that we can use. You can use any of 2, right? So let's move into the converging lens. Oh, I know that this color is not good, but since I started, I will go with that. So that is my lens, and this is my optical axis. This is the line that I'm talking. This line is the center, go through the vertex point of the lens. That's where we're going to draw the ray. So now I have a focal point here, they are same distance, and I have 2 centers, center here and center here. So it is very important that if you use the object on the left side, make sure you make a box what is your important focal point is, then you will not going to mess up your drawing. Okay, so now let's say I have object, I'm going to use somewhere here. I have object somewhere here. So now I need to draw 3 rays. First ray is parallel light go through the focal point, right? So you just draw a parallel light that should go through the focal point. My focal point is other side, that I'm going to draw like this. That will be number 1. Now in mirrors, it reflect back. Here it is possible to go to other side. That's different. Okay. So now second ray will be exactly opposite to this one. What is the opposite to this one? You need to send to the focal point, and that should go through the parallel to the axis. Do it. It's very hard to draw. I'm going to draw like this. Should be a straight light, although it is hard to draw it in here. And then you're going to extend this light or draw a parallel to the axis. That is my second ray that you can draw. Okay. And then our third one is easier. Third one is go through the vertex point, will be keep continue on that point. Okay, so go through the vertex point, will be just keep continue. Okay, so my drawing seems better in this time. So you're going to keep continue, that will be your ray number 3, right? So now I started from this point, where I end up, that tip point is here. But those are actually real rays that I can use the solid line to represent the image. This is image, this is object. You can use any 2 of these to draw or find the image location in graphical. Okay, so theoretically we can use the equation that we discussed. Okay. So now let's take a look on different position of the object. Now this is my object is somewhere away from the center. So now you try to draw 2 rays, whichever 2 you can draw, these 2, and you find the image somewhere here, right? Upright, smaller in size, and real. And this one, you have exactly 2F position object, and then first ray, and then second ray. So you found inverted, same size, 2F, but on other side, and it is real. Okay, and let's move into the next one. I have object in between 2F and F. So now first ray and second ray and third ray also there, and then I found the larger in size object is inverted and real. And then at F, it's very important case. These 2 lines will never meet. This is where you're going to watch your eye. This is where your eye is, right? So these 2 lines will never meet. That means no image in this case, similar to your converging I forget the image. Similar to your concave mirrors. And so now object is inside F. So now take a look what will happen. First ray and second ray. So these two will never meet on the right side, but they're going to meet on the left side. This is also very specific, a special case that you can use the converging lens as a magnifying glass. Okay, so you will see in this case upright, virtual, larger in size image. Okay, so now final conclusion of converging lens will be depend on your location of the object. It will create the image in different places. You will going to see virtual image, real image, smaller in size, larger in size, inverted and upright images depend on the place of the object. Okay, similar to your concave mirror behaviors. So now divergent lens. So divergent lens will be simple. So I have lens diverging, and then I have optical axis. I have my vertical axis, and again I have 2F. If you have object on the left side, your important focal point will be left side one. Okay, so now you're going to keep the object somewhere. I'm going to draw it in here, and then my first ray I'm going to draw my parallel ray. So first one is parallel ray. What happened to this one? In this one, you should not bend in towards this direction through the F, because this is where my focal point is, important focal point. This will go diverge as this first ray. And second ray, you need to go through the focal point, but remember that you should go through the other focal point, and then that will be a parallel ray. So that means I need to send the light similar to going through the focal point on the other side. So, but it will not go to the focal point. What happened is when it hit the lens, that going to go parallel to the axis. This is your second ray is. So then if I extend those dots, that is bad extension. So if I extend those dots, this is where you're going to find your tip point, right? So then third one also you can draw easily. Third one is going through the center. It will just keep continuing. So that will be exactly go in that point, and then you're going to create your image somewhere in here. Okay, so now for the divergent lens, it will always create virtual image, smaller in size, images in between F and the lens, and it is upright if you have upright object. Okay. So now by watching the other drawing, you can see that. So let's do this. Object is outside of the 2F. You draw your two rays, and then you're going to see the image, extended light somewhere there. It is still upright, smaller in size, and virtual. And the next one, upright, smaller in size, and virtual. And third one, upright, smaller in size, and virtual. And next one at F, even at F, you will going to see the image in diverging lens, upright, virtual, and smaller in size. And then inside F also, you're going to see the image almost same size, virtual, and upright. Okay, so what that means is by using diverging lenses, you going to observe same kind of image. You just going back and forth of the going back and forth according to the location of the object. Other than that, there is no deviation of the other things. Always upright, virtual, smaller in size will be the image information for divergent lens. Okay, so now summary of lenses. Divergent lens, F is negative. Convergent lens, F is positive. Divergent lens always create virtual image smaller in size, and Converging lens can create virtual or real in large or small. This will be features similar to the mirrors, right? Diverging lens will be similar to the convex mirror. Converging lens similar to the concave mirror. Okay. Okay, so that's about it. So we're going to do some calculation in your recitation session and some drawing again to practice those concepts. Okay, so now application of converging and diverging lens. You guys know that we have microscope, telescope, and eyeglasses. These all are according to the accommodation that you need for the eye. We need to use converging and diverging lens according to that. Okay, so there are many applications on those. So let's stop here.